Welcome. In this segment, we look at a couple of examples where we calculate the point elasticity of demand. It's simply a matter of applying the definition and doing the differentiation involved. So, typically they give you the demand equation either in the form Q equals a function of P or P equals a function of Q, and then ask you to calculate the elasticity of demand at some set value of P or Q. And depending upon which way equation is given, the demand equation is given, you would use either this formula, so either this formula or we can use this formula. Okay. In this problem, Q is given as a function of P, so we'll use the first version. We start by calculating dQ over dP. To do that, I write the square root as power 1/2. And now I have to use the power rule and the chain rule, differentiate for the exponent 1/2. So I get 1/2 times whatever is inside to the power 1/2 minus 1. 1/2 minus 1 is a negative 1/2, giving us this. Times derivative of the inside, which is 0 minus 2p. Of course, you can simplify this a little bit. This is just minus 2p. We can cancel the 2's. Or you can just plug in the given value of p into this as it is and then simplify that. This will come out to be 30 to the 30 squared to the negative 1/2. So we get negative 2 times 40 over 2 times 30, which is negative 4/3. Remember this derivative, or dP over dQ, should always be negative. Because to calculate eta, I also need to know the value of Q. So we take the demand equation, plug in 40 for P and calculate the demand, whatever the units are. The units don't matter for eta because dQ and Q have the same units, P and dP have the same units, so all the units will cancel. Now we are going to plug in all these numbers, negative 4/3 for the derivative dQ over dP, 40 for P, 30 for Q into our formula for eta and calculate what it is. It comes out to be negative 16 over 9. Its absolute value of 16 over 9 is bigger than 1, which means the demand is elastic. It means that if the price is increased by a small percentage, demand will go down by a percentage which is larger than that. So 1% increase in price will produce a decrease in demand of more than 1%. In this case, 1% increase in price produces almost 1.7% decrease in demand. So the demand is elastic. The other way in which the demand equation can be given is in the form P equals a function of Q. And in this case, we'll use the alternate version of the formula to find the point elasticity of demand. So the alternate version of the formula is P over Q divided by dP over dQ. So I'm going to start by calculating dQ or dP over dQ. So we need to differentiate this. It's an exponential function. 100 is a constant factor, so I keep it as it is. Derivative of the exponential is the same exponential because the base is e, times derivative of the exponent. The exponent is negative 1 over 200 times q. So it's a constant times q. The derivative is just that constant. Because again, we can simplify this a little bit, or we can just plug in 200 the way it is and then simplify that. Of course, 100 over 200 is 1/2, and in the exponent, negative 200 over 200 is negative 1, and I still have this negative there. Of course, we also need to calculate P when Q is 200. So we plug in 200 for Q in the price, the demand equation, and simplify that. That gives me 100 e to the negative 1. So we have then P over Q, and plug in these numbers for P and 200 for Q, this for dP over dQ, the formula for unit for the demand, for elasticity of demand, excuse me. So now 100 over 200 is 1/2, e to the negative 1's cancel. So it turns out the whole thing comes out to be just, there's a negative missing, so it should be -1. There is a negative here which should still be present here. So it has unit elasticity. We'll see what this means in general terms in the next chapter. So bye for now.